Good day. In this video, I will explain how to use Gauss's law for a spherically symmetric distribution, but I will refer back to my previous video, which explained how to evaluate the left-hand side of Gauss's law. So other than this, we will do a few examples. Okay, so let's start by writing Gauss's law. Just a second, I need a pen. Okay, so we'll have Gauss's law. And the equation that states Gauss's law of electrostatics is as we've seen in the previous video, it looks like this. Okay, so this is a flux integral. Let me put an S here. Sometimes they do that. Okay, so this is a flux over a closed surface. Closed surface. And the important part on the right-hand side, and that's what we're going to deal with in this video, is that this charge is the charge that's enclosed within that closed surface. Okay, so let's write that down. So Q enclosed, enclosed within that closed surface. So within closed surface. Okay, we're going to deal in this video with spherically symmetric charge distributions, and we're going to analyze that situation a little bit. Okay, so let's keep going and see what we can come up with. Okay, let's do the simplest example first, which is not trivial like the point charge, which was already done in the other video. Here's the origin. Okay, and we have a sphere around the origin. Okay, and we have rho, which is a homogeneous charge density. Okay, so homogeneous charge density. So let's solve this problem first. Okay, and in this case, so let's say this is not a good sphere, admittedly, but capital R is the radius. Okay, let me draw a better sphere. I'll try. Okay, maybe for sure I can draw a bigger one. Let's do it like this. So yeah. Okay. Well, I missed kind of. So here's a hopefully better sphere. Okay. Okay, and the point is that we're going to take a Gaussian surface. Okay, and there are two ways to take one in this case. Okay, one is if R is smaller than capital R. Okay, and in that case, your Gaussian surface may be like this. Okay, so that's just an example. And that's also a sphere with the one indicated by dashed lines. And that sphere has a radius which is smaller than capital R. And what that's going to be enable us to do is to calculate the electric field at a distance from the origin which is smaller than the radius of the object. Okay, so let us do this one. Okay, now again, here's our Gauss's law, but we already I shouldn't have to write this because we already know. Okay, so we already know this for because we figured it out in the previous video that in this case the left-hand side of Gauss's law becomes ERR 4 pi r squared. This formula is going to be true for our second part of this exercise when the Gaussian surface is outside the sphere, okay? But in that case, we have to keep in mind that r, small r is outside the sphere, so small r is greater than r, and the enclosed charge will in general have a different formula, okay? So now we want to calculate the enclosed charge. Well, keep in mind that we have a homogeneous charge density rho, and the enclosed charge is what I'm indicating by this shade, which is within the small sphere. Okay, so the enclosed charge in this case is not the full charge of the object, which would be 4 pi capital R cubed divided by 3 times rho, but only the volume of the small sphere. That's the volume of the small sphere times rho. Okay, so that's actually the enclosed charge within this Gaussian surface, which is a sphere concentric with the large sphere with a radius that's smaller than the radius of the object. Okay, and now we can put this together and look what happens. So we have the flux integral, which we evaluated from before, and we have Q enclosed, which is 4 pi r cubed divided by 3 times rho, and we of course need this epsilon 0. Okay, so this is actually our important equation. Okay, and we can cancel the 4 pi on both sides, and we can cancel some of the r's but not all of them, and our final result is radial component as a function of radius. Okay, and it's equal to rho r divided by 3 epsilon 0. Okay, so this is the electric field, the magnitude of the electric field, if r is smaller than capital R. Okay, so that's one important result that we are able to get. Now let's go on and let's do the case when r is greater than r. Okay, so in this case, what you have to do is, let's say here's your sphere. Okay, let me see if I have shapes here. I must have shapes. Let's try it like this. Okay, so I have a shape, but I won't be able to make it concentric so easily. Okay, so here's my sphere. So this will probably be better. I don't know. I haven't tried this yet. So okay, so this has a radius of r. Okay, and what I want to do is define a Gaussian surface, which has. Okay, I'm gonna put it here. Okay, but I'm going to change something about it, if I can. What do I want to change about it? Font, no. Just a second. I'm trying to make it dashed line. Yeah, I can do that. Here we go. Okay, so now I will move this. It's a circle. Oh, I didn't mean to do that. You know what? Okay, then I have to. Okay, I have to make another circle. Let's make another circle. So let's forget about this circle. Let's erase all this. Okay, but will put a new shape. Nah, come on. Sorry. So it's gonna be a circle. Okay, that's circly enough. Let's make this a solid line, and now move it here. Okay. Now it's not perfect. I don't know why. But the idea, okay, that looks good. Okay, now what do we want here? What am I trying to represent here? So I have a sphere, okay, which I'm representing by this circle, and the radius of this sphere is r. But my Gaussian surface, so recall now that we are outside of the, my Gaussian surface has a radius of small r, okay? And um, so now again we write Gauss's law, but the left-hand side of Gauss's law we already know. The left-hand side of Gauss's law is ERR 4 pi r squared. We figured that out in the last video, and we already used it in the previous part of the exercise. But here I'm going to need, so now if you take the enclosed charge, okay, and if you look at this carefully, you see that all of the charge of the sphere is enclosed. Okay, so how much is the enclosed charge? Well, in that case, it's the volume of the sphere, which is 4 pi capital R cubed divided by 3 times rho. And of course, we have to divide by epsilon 0, which was that constant, which in this case just goes along for the ride. Let me make this a little bit more aesthetic, what I wrote here. Okay, and now we do a comparison with the previous part of the exercise. Okay, so where's the previous part of the exercise? The big difference was the formula for the enclosed charge. Okay, so in this case, small r is smaller than capital R, and only some of the charge on the sphere is enclosed within the Gaussian surface. On the other hand, here in this part, small r is greater than capital R, and all of the charge on the sphere is enclosed within the Gaussian surface, because the Gaussian surface is actually this one. That's the Gaussian surface. Okay, and this here is the surface of the object itself. Okay, that's the surface of the sphere. Okay, so now we can rearrange this, and we find that the radial component of the electric field, which is the only component there is, we can cancel the 4 pi, but we can't cancel the r's, because here we have rho r cubed divided by 3 epsilon 0 times r squared. Okay, so that's our result for the electric field outside. Okay, let's put these two results together and do a little bit of investigation. So we have ERR, and we have two formulas. One is rho rho r divided by 3 epsilon 0, and this was valid if r was within the sphere. Okay, and the other one was rho r cubed divided by 3 epsilon 0 r squared, and this was valid if r was greater than the radius of the sphere. Okay, so basically what you have, let's try to picture it. So that's the final result for the electric field, because there's only a radial component. Let's try to picture it. Okay, now, and I'll use a shape again. So suppose that here's the sphere that we are talking about. The electric field is always pointing radially outwards. Okay, but its magnitude depends on how far you are from the center. Okay, so let's see. The magnitude of the electric field, I didn't draw that very well actually. I could try again, but I'll just tell you the story. If you look at this, the magnitude of the electric field, we can plot the magnitude of the electric field. Okay, so first of all, we can say, we can introduce a coordinate system, R, and on that coordinate system, we have the radial component of the electric field as a function of radius, and we have one special point that we are curious about. Okay, what happens at that special point? And what? Well, we see that in R, the radial component of the electric field is linear. Okay, so it's some sort of linear function. Okay, which has a slope. The slope is given by rho over 3 epsilon 0, as we see here. And what happens at R equals R? That's important, actually. So if we have R equals capital R, well, this is rho capital R divided by 3 epsilon 0. If I substitute capital R for small r, I get the same thing for the outside component also. That actually means that the electric field is continuous. Okay, so it's going to outside the sphere. It goes as 1 over r squared, right? So it's actually proportional to 1 over r squared. So I don't know, something like this. Okay, so here it goes as r, and here it goes as 1 over r squared. But the important thing is that if you can approach this point from below, or you can approach, and if you wanted to approach that point from below, you would have to use this function, and you could approach that point from above, for which you would have to use this function. Okay, and we see that both of those tend to the same number. So here the value of the electric field is rho r over 3 epsilon 0. Okay, so rho r over 3 epsilon. Oh, sorry, I didn't know that that was going to happen. Let me write it here. Rho r over 3 epsilon 0. Okay, so this is important. We calculated that within the sphere, the electric field grows as r. Outside, it decreases as 1 over r squared. Now, another interesting thing that you can derive from this is sometimes it's actually presented as a law of physics in certain textbooks, especially in the case of mass, because gravity is a similar similar to the electric field. You can define a gravitational field. But let's see. So for r greater than capital R, we had that ERR is equal to rho r cubed divided by 3 epsilon 0 r squared. And instead of this rho, you can write this in terms of the total charge on the sphere. And the total charge on the sphere is the volume times the charge density. That's equal to Q. Okay, so let's write this in for this electric field. Okay, so we see that rho is actually equal to 3Q divided by 4 pi r cubed. That's a cube. And if we make this substitution in here, surprise, surprise, look what we get. ERR is Q divided by 4 pi epsilon 0 r squared. Okay, you see that the 4 pi remains, but the 3 cancels. Okay, and the r cubes are also canceling. Okay, so outside, so this is an interesting statement that, okay, we have a charge density. Again, let me draw a sphere. Okay, that's not a sphere, sorry. So let's draw a sphere. Well, whatever, that's our sphere. And we have a homogeneous charge density, rho, which means that the charge density is smeared homogeneously all around the sphere. Okay, But if you're outside the sphere, all you see is a point charge, because this electric field is the same electric field that a point charge would have if it was situated here at the center of the coordinate system, or the center of the sphere. Okay, so that's one interesting thing, and this is actually true for any spherical charge distribution. If you're outside it, so rho could have had an R dependence, um, you would still get this result, that you could concentrate all the charge in the center and get the electric field, um, but that would only be valid outside the object. Okay, so outside the object. Okay, so that's one part of this example. Let's make the example a little bit more interesting. What we will do is the following, because I just want to put emphasis on this. We have a sphere. Okay, so I won't draw spheres. I'll produce one like this if I learn how to do it. Okay, so yeah, there we go. That's a nice sphere, isn't it? Okay, so here's our sphere. Okay, and what we're going to say is that this sphere has volume charge density rho. Okay, so this rho is the volume charge density. Okay, just like before. Density. But in addition to this rho, our sphere on the surface, so like, here, is going to have sigma, which is surface charge density. Surface charge density. Okay, surface charge density is not simply a thin layer of volume charge density. It's when charge is really, really concentrated on a surface. Okay, so that's what we mean by surface charge density. It's mathematically a slightly different object, and that's what we want to explore here. Okay, so now the point here is that the total charge on this sphere, okay, so let's just play with that first. So the total charge on this sphere is equal to, well, it's going to be the volume charge density. Sorry, I forgot to say, but the sphere, as always, has to have a radius, and that radius is capital R, okay? And the point is that the total charge on this sphere is the charge originating from the volume charge density, also the charge that originates from the surface charge density. And how much is that? That's going to be the surface charge density times the surface of the sphere. Okay, so this is the total charge. Okay, I know, maybe we want to call this Q rho, or Q rho, and we can call this Q sigma. That sort of indicates their origins. Okay, but now we want to calculate again the electric field. Okay, so again, I'm going to draw a circle. Okay, and that's supposed to have radius R. Okay, and what am I going to do? I'm going to first, so again, it's radius R. It doesn't scale as the previous one. Okay, but first I'm going to say rho is smaller than R. Okay, so that's my Gaussian surface inside the sphere, like that. And you know that, okay, not much surprise, because you know that the left side of Gauss's law in this case is 4 pi r squared ERR. Okay, so that's the left side of of Gauss's law in this case. And the charge included has nothing to do with the surface charge density, right? Because this sphere, let me try to draw those spheres a little better, bigger. Okay, so here's one of them. And this is the Gaussian surface for this. No, that's not. Let's draw another circle here. But this circle, let's make it dashed line and let's move it. Okay, so okay, and now you see that the surface charge density is all out here. Okay, so that none of that is inside the Gaussian surface. So everything, this part of the problem is exactly the same as before. So in other words, the enclosed charge is given by the same formula as before. Let me actually move the board a bit and write the enclosed charge as 4 pi r cubed divided by 3 r cubed divided by times rho, and I'm going to divide that by epsilon 0. Okay, and from this you can easily figure out that the radial component of the electric field, as long as we are within the sphere, just like before, is rho r divided by 3 epsilon 0. Okay, so that's a start. Now, what about when we're outside the sphere? Okay, so let's try to draw that. So I will draw these spheres the other way around. Okay, so I'm going to have now one sphere. Sorry, I'm trying. Okay, so I have one sphere. Okay, this I don't care about. Let me put it here. Yeah, okay, whatever. I'm going to make this sphere a little bit smaller, but I'm going to change this one to solid line. Okay, and now I move this sphere inside here. Okay, what I'm trying to represent here, hopefully with success, at least with some, is that now we're outside. In other words, that's the radius of the actual sphere, and this is small r, the radius of the Gaussian sphere. And now the Gaussian sphere includes the charge density. And look what happened. That you kept. Let's say if you keep, here's your sphere. Okay, so again, this has radius capital R. Sorry, I'm going to try to draw that again here. So this has radius capital R. This has radius small r. Okay, but here the small r circle, which is the Gaussian surface, is within the sphere. Okay, but all of a sudden, when we kept increase it after capital R, we're outside, and that now includes the volume charge density and the surface charge density. In other words, if we apply Gauss's law, we will have 4 pi r squared e r r on one side, okay, and that's going to equal, well, the total charge is now included, so you could write q total divided by epsilon 0, or as we have written up there, qr plus q sigma divided by epsilon 0. Okay, so there's more than one way to write this. Let's write it using the actual formulas that we figured out here. Okay, so we can also write that this is equal to 1 over epsilon 0 times 4 pi capital R cubed divided by 3 rho plus 4 pi capital R squared times sigma. Okay, so these are all valid formulas for the electric field. And if you actually solve this equation, by solving, I mean solving for the electric field, look what happens. You will have E R R is equal to 1 over epsilon 0. I just keep this like this, but because what gets cancelled is the 4 pi. Okay, so I'm going to have here this term 3r squared plus this term, which is sigma r squared over r squared. Okay, so what I did here is solve for this equation. So solve for this variable, actually, the electric field, which is this object here. So I just divided by 4 pi r squared. Let me actually write this in yet a slightly different form. So I'm going to write this like this: rho r cubed divided by 3 epsilon 0 plus sigma r squared divided by epsilon 0. Let me move this up like this. This is epsilon 0, sorry. Okay, and that's divided by r squared. I wanted to write this in this particular form because this here is a constant. So we have an electric field which is divided by r squared. Okay, so it goes as 1 over r squared. No, not the electric field is not divided by r squared, but it goes as 1 over r squared. Okay. Alternatively, you could write this as Q total divided by 4 pi epsilon 0 r squared, where Q total is what we have figured out already. We have used it here, but we figured it out earlier up here. Okay, so this is the Q total. I don't know if I wrote total or just TOT. Let me check. Yeah, sorry, I meant to write here. What's going on? Sorry. Q total. Okay, and what did I do up here? Well, this should have been a total, also TOTAL. Okay, now what I wanted to do is again draw the electric field as a function of r. Okay, and we showed that within the sphere it's not very different, right? It's not different at all. This is within the sphere. Okay, but and outside the sphere it's a 1 over r squared potential, but this number is no longer the same, right? As it was in the case of no surface charge density. Okay, so when you have a surface charge density, your electric field, so radial component of the electric field as a function of the radius. So here's the r variable, that's the electric field, and let's say r, this is a special point that we need to understand. So first of all, it goes up. Okay, now, however, the interesting thing is, so let's go back to our, let's go here, and if I substitute r equals r here, the electric field I get, based on this formula, is rho capital R divided by 3 epsilon 0. Okay, so based on this, what we can write is that ER, as R goes to R from below, that's the notation that's used for this, is actually rho R over 3 epsilon 0. On the other hand, looking at the other formula, which is valid for the electric field when R is greater than capital R, we see that something interesting happens. Okay, so if I substitute r squared for this small r here, what do I get? I get that in that case, well, let me go back up here. So if I substitute r equals capital R, what do I get here? I actually get rho r over 3 epsilon 0 plus sigma over epsilon 0. Okay, that's what we get. Okay, so what we can say is that ER, as R approaches R from above, that's the notation that's used for that, is one term which is exactly the same as the previous one, rho R over 3 epsilon 0, but due to the surface charge density, we get another term. Okay, so here we are going to have rho R over 3 epsilon 0 plus sigma over epsilon 0. What this means is that the electric field is no longer continuous at R equals R. If you approach capital R from below, you get a certain number, but if you approach it from above, you get a different number. Okay, so in other words, and it's going to be proportional to it's going to be proportional. So there's going to be a jump, a discontinuity in the electric field here. After, it's going to go down as 1 over r squared, like before. So here it goes as r, like before. And this jump here, that jump, let's say I'm going to call it delta E. Okay, so this delta E, the jump, is given by the surface charge density divided by epsilon 0. Surface charge density divided by epsilon 0. Okay, so there, I really should, this looks like delta energy. I hope that doesn't get confusing in that sense. What I mean here is that there's a jump in the radial component of the electric field, which I'm calling delta ER. Okay. Okay, so these are two important things that one can get basically from Gauss's law. Okay, and to finish this video, let me do one other example. I'm going to say that rho, the charge density, varies as alpha, which is a constant, times r. Okay, and this is for r smaller than r, and it's going to be 0 if r is greater than r. Okay, so let's do this and solve for the electric field in this case. Okay, so that's what we want to do. Okay, based on Gauss's law. Okay, so once again, so we're going to have a sphere, and we have two regions. Okay, so let me make a sphere. No, that's not what I wanted. Okay, so I'm making a sphere. Sorry, I have to start that again. Man. Sphere, sphere, sphere. So I have a sphere like this. Let me erase the unnecessary spheres. Okay, and I suppose I can move this sphere to a different location. No, I erased it, sorry. Okay, so here's my sphere again. Okay, and I'm going to first do the case when r is smaller than capital R. Okay, and the point is the left-hand side of Gauss's law looks exactly the same. We can write ERR 4 pi r squared, that's an r, and that's the enclosed charge divided by epsilon 0. Okay, and now the big question is, how do we get the enclosed charge, which is the charge that's inside that sphere. Okay, and to get the enclosed charge, what you have to do is do a volume integral, and the volume integral looks fully. If you were to write it fully, it would be the volume element times rho. Okay, but the volume element, so we have a three-dimensional integral here. It's r squared dr. Sorry, I have to restart this. Let me do it here. So the volume element is integral r squared dr sine theta d phi, and d theta also. Sorry, I forgot d theta. Let me actually put d theta before this. D theta d phi. And we need the charge density, of course. And the charge density is given by alpha times r. Okay, so this is rho, which is the r-dependent charge density. Okay, so that's the problem that we are trying to solve here. Okay, so here's our charge density. And of course, this is a spherically symmetric problem. You see that. Okay. And what we have to do here is integrate, but sorry, I have to do a relabeling. I'm going to relabel this r, because it's the running variable, as r prime. Okay, because, sorry, I forgot that r is going to be the radius of my Gaussian sphere. So that variable is already taken. Okay, so this variable here is already taken. Okay, now we have to do this integral. Okay, and the phi goes from 0 to 2 pi. The phi goes from 0 to 2 pi. The theta goes from 0 to pi, and r prime goes from 0 to small r, because this is the enclosed charge within the sphere of radius small r. Okay, and now we have to evaluate this integral. I'll just tell you quickly that the angular integrals just give you a 4 pi. And what you're left with is 0 to small r, r prime. Sorry, this r should have a prime on it as well, to the third dr prime times alpha. Okay, so alpha is a constant, so I could pull that out in front of the integral. So what we get is 4 pi alpha times r prime to the fourth divided by 4, and that goes from 0 to r. Okay, and that is actually, you can simplify that and substitute in the limits, so you get pi alpha r to the fourth power. Okay, so that's the enclosed charge. That's the enclosed charge. And now we can put our Gauss's law together. Okay, that's the left side. And on the right side, we should have enclosed charge pi alpha r to the fourth divided by epsilon 0. Sorry, that epsilon 0 is not very nice, but so I'll try to fix that. Okay, so epsilon 0. And you can simplify this, right? You can certainly simplify this and get ERR equals, the pi cancels, alpha r squared divided by 4 epsilon 0. Okay, so there you go. But this is only valid for r smaller than capital R. Now, in this problem, there is no surface charge density, is there? Okay, so no surface charge density. So we expect that the electric field is continuous. So right now, the electric field that we found, sorry, I'm not going to have time to do the rest because it's a 45-minute video. So I'll sign off now and I'll leave it as homework, the outside part. But you need the total charge and divided by 4 pi epsilon 0 r squared. Okay, so it's going to be something like this, a continuous function like this. Thank you very much for your attention.